Good afternoon, this is Schweitzer, and this is a review on what I call linear properties of states of matter. Um, this isn't just individual topic, it's got wide-ranging effects pretty much all through chemistry. So whenever we're looking at a particular mathematical formula, you want to be somewhat aware of is this a linear relationship or is it going to be reciprocal? This is probably 95%, and if you include in y equals x squared or some sort of exponential scale like a logarithmic scale, then you'd be base 10 even, you'd be at we're talking 99% of what we're doing here. So majority of this stuff is linear relationships. This is just a factor label. And, and I know kids understand what they're doing when they flip back and forth between proportions and factor label, whichever happens to suit them best. The factor label is just a way of doing a proportion. That's this guy. So, for example, P1V1 over T1 equals P2V2 over T2. This has both the linear and it has the reciprocal relationship. So these two, for example, are representing a linear relationship. So meaning that if I double my temperature over here from like say 10 to 20, then this will double from 1 to 2. All right, so then we have this reciprocal relationship, which means that if x increases by 2, then y has to decrease by 2, or has to increase by 1/2 or decrease by 2. So that's it. As long as you recognize that that's a relationship, then you can do lots of estimating and things of this nature. Okay. So we'll highlight some of these relationships here and maybe point out a few places they occur in the chemistry that we're dealing with. All right, so two rigid 2.2 liter containers, so same volume, 2.2 now. Again, it's a common volume because 22.4 liters equals 1 mole, which means if we're at STP, and I don't know, maybe we are, maybe we aren't, doesn't matter. Whenever I see 2.2 liters, my brain's immediately clicking to 2.2 liters equals about 0.1 moles. So just kind of think about that. All right, so two rigid 2.2 liter containers, O2 and the other F2 at 25 degrees Celsius or warm to 50 degrees Celsius. Answer the following questions. Okay. Now, all the following atoms are traveling the same speed in the 25 degrees Celsius container. Justify or nullify. Okay, so this isn't all just relationships. We're doing lots of states of matter here, things of this nature. Now, first things first, the answer is, it says, answering questions, all of them are traveling the same speed. This is a big no. Whenever we talk about temperature, we're talking about average kinetic energy. You'll see that little chart right here describing that. And so in this situation, some are traveling very fast, some are traveling very slow. You might see a box. I've seen this on AP exams where they have one particle traveling really fast. The arrow represents the speed. Another one traveling, moderate, and another one traveling kind of slow. So and one it may not be traveling at all. Okay, it's just sitting still. So in this case, they aren't all traveling the same speed. Temperature does reflect velocity, it does reflect kinetic energy, but it's an average, some high, some low average. The space between the particles do not change as the temperature due to increasing temperature. Justify or nullify. This is a justify. Because it is a rigid container, and the container is not expanding at all, then the total volume between space between particles is constant. Small detail, but I've seen it come up. Below, you'll find a Maxwell's distribution of particles at 0 degrees Celsius, or sorry, at O2 at 25, and a second line representing 50. Okay. Again, as we go through this, of course, you're trying to pause the video and try on your own what should look like. All right, so we have 0. There's always a particle thing, so we have to start at 0. And I know the particles on average will be traveling faster. So I also know that the area under the curve here represents, the total number of particles. So I want this area to be conserved. So I'm going to do this. I'm going to have to stretch it out and do a real good job there. This should be going towards 0. There we go. Now I didn't get as high because I needed to still start at 0. Right? So this would be the 25 degrees Celsius, and this is the 50 degrees Celsius. Okay. I think that's basically it. All right, so the next one says you will find Maxwell's distribution particles of O2 as second line representing the F2. Okay, so now, good question. So here, kinetic energy equals 1/2 mass velocity squared. Both these particles have the same kinetic energy, but the F2 has a larger mass. Okay, you can see that right here in the sense that here is oxygen, here is fluorine. So fluorine's a little bit heavier because it has another proton and maybe another neutron. All right, so in this case, because it's got a heavier mass, its velocity will travel a little slower. If this is O2, I then, and the same number of particles, by the way, so I would want to maintain my height, just the opposite of the last one. I might do something like this. All right. Trying to keep the area under the curve about the same. All right. There we go. I've seen this in multiple choice questions. All right. Student hypothesis, the pressure in the O2 container is higher the larger frequency of collisions. Justify or nullify. Okay, I'm going to nullify that. A couple of ways you could do that. PV equals nRT, and I'm solving for P. P equals nRT over V. All of these factors are identical for each container. Therefore, the pressure should be the same for each container. Now again, yes, we do have more collisions with the O2, but the fluorine particles may have less frequent collisions. All right, so they have less collisions, but the collisions that do have are more forceful. So, there we go. Therefore, the pressure is the same. All right, student hypothesis, the pressure in the warm container is double the pressure in the cooler container, just for nullify. Now, we are going from 25 degrees Celsius to 50 degrees Celsius. Now, I did mention that P1V1 over T1 equals P2V2 over T2. And then if you double your temperature, you will double your pressure. But we're not actually doubling our temperature. This is 298 Kelvin, so this is a very common question. 273 plus 50 is 323. All right, so in this case, 323. And of course, you should, if you realize this is a proportion, x1 over y1 equals x2 over y2, then in this case 327 over 298, that fraction is It's 323, by the way, not 327. 323 divided by 298 is 1.08. So the temperature has increased by a multiple of 1.08. So my pressure should also increase by a fraction of 0.08. I've seen problems in the past where they would use just that fraction to show what proportion to show how things increased. So my temperature is going to go up, my pressure will go up some, but it's definitely not going to double, just a little bit more up. I've seen multiple choice questions where they want you to just pick out the one that's slightly larger. Number 2, a 10 milliliter solution of 6 mole hydrochloric acid is diluted to 30 milliliters with distilled water. Okay, so in this case, we're using M1V1 equals M2V2. All right, and my volume is increasing, in this case, by 3 times. So this is a reciprocal relationship. So that means my molarity must drop by 3 times or increase by a third. So 6 divided by 3, my new concentration is 2 molar. No calculator. How much water is added? Okay, so in this case, pretty easy. This guy starts out at 10. This guy ends at 30. So I just added 20 milliliters of water. All right, so very useful skill here. We have a beaker containing these concentrations. What's the concentration of each of these guys? 0.5 times 2 is 1 molar. 0.5 times 1 is 1 molar. 0.5. 0.5 molar. All right. 20 milliliter solution of 0.2 molar NaCl reacts with 20 milliliters of 0.2 molar lead nitrate, causing precipitation of lead chloride. Write out the balanced equation. Okay, so you can write out the whole thing. Would be NaCl plus lead nitrate yields lead chloride. I'm going to just do the, let's do the whole thing here. NaCl plus PbNO3 yields PbCl2 plus NaNO3. All right. This guy here is, which one's a limiting ion? Okay, so now, 2 things that create are limiting. These are all proportions. This is stoichiometry, this is states of matter, this is proportions. All right, so in this case, there are 2 things. One, rate use. So we've got to balance this thing out here. So 2 nitrates. So I'll put a 2 here and a 2 here, and we're done. Okay, so this guy is used up twice as fast. Now, I want to know quantity, my other one. So moles is molarity times liters. So molarity is equal to moles per liter. Okay, multiply those together gets you moles. All right, so multiply it together here. Okay, so now let's look at we're at for concentration. They're both 0.2 molar, and they're both 20 milliliters. So these guys had the same number of moles. This one's usually twice as fast. Bingo. This is my limiting reactant. And if you look at my net ionic equation, because we know these things aren't actually together, it would be Pb plus Cl negative plus 2 of them will produce PbCl2. Many of you are probably looking to see, okay, rate used. You could just look at this thing, 2 chlorines for every 1 lead. That's what's happening. So someone else might not need to write this equation. They look at what's happening here and say, oh, okay, twice as fast as that one, because that's the precipitation rate. Okay, so which one is going to be the limiting ion? It's going to be the chloride ion. 2 of those we consume for every one of these. All right, determine the concentration of the following solution. Again, no calculator because we're using proportions here. Now, this is a super common multiple choice problem here, where, got ahead of myself here a little bit. Okay, so where they'll just give you the answer, and you know, 4 different options, you pick it out. So a lot of times I like to use my spectators to whittle things down. We know the spectators aren't precipitating. So right now, and I've already listed all my concentrations above here. I think I have, did I do that one or no? Let's see what I did here. I did not. Okay, so I'm going to add a little to this one. Let's do these ion concentrations before. I like to do this before and after. This would after would be the actual answer to the question, but even before. So 0.2 times 1 is 0.2. 0.2 times chlorine is just 0.2. And then 0.2 times 1 is 0.2. And then 0.2 times 2 is 0.4. All right, and afterwards. Okay, so now first of all, we're doubling our volume here. Because I'm doubling my volume, 20 milliliters and 20 milliliters, I'm cutting all my concentrations in half. Okay, now you can use M1V1 equals M2V2, or you can just use proportions here. This would be 20, this would be 40. This is going up times 2, this has to get dropped by 2. All right, so this is going to just kick over to 0.2. It's a spectator. The sodium will be 0.1. All right, now, what about these two guys? Well, the chlorine, first of all, is limiting. It's going to be gone. It's going to 0. The lead, you'll note that because it's 2 to 1 ratio, for every 2 chlorines, I need 1 lead. So I'm going to cut half of it down just by consumption, precipitation down to as a solid. And then I'm going to double the volume, so I'm going to go 0.05. And that's what we want. In the beakers below, draw the proportions here. Okay, so, all right, so I'm going to go Na plus Cl minus. I'm going to draw 2 of them just so I can make it through one cycle of the reaction without having to split a molecule in half. Here I want the same concentrations. I'm going to go, because they're both 0.2, so here Pb2 plus, Pb2 plus, nitrate, 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 and negative equals NO3 minus. All right, so sometimes I circle them as I write them out here, but the lead will grab a chloride and a chloride to produce a solid lead chloride. And then in solution, I still have my 1, 2, 3, 4 nitrates. Those are all my nitrates. And then I have 2 sodiums here. I'll work those out. Na plus, Na plus. And then 1 lead is an excess. That should be here. Pb 2 plus. There you go. Pretty common style of question. They're not going to have you draw anything, but multiple choice wise, if they have 4 options, so you can easily pick which one matches up. Sometimes an ice table works so nice there too, but either way. The reaction of 50 milliliters of this concentration is added to a beaker with 50-gram piece of zinc. Draw a proportional diagram before and after. All right, so before we do this problem, we kind of got to know the reaction here. So it's going to be copper. This is the reaction I'll use. I think on an AP test, they would give you, they wouldn't expect you to memorize a specific reaction. So they likely would give you some indication what the products are. But we don't need that here, I guess. Zinc, metal. The zinc will exchange with the copper, forming, that's right here, zinc 2 plus. And then we'll have, in this case, let's just back up here a second. So the copper will become copper metal. Okay, let's just do that. And then the zinc becomes zinc ion, so zinc NO3. You should at this point be able to recognize that this is an exchange of electrons between the metals, and the nitrate had nothing to do with it. All right, so what do we have here? It says we have 50 milliliters of 0.5 molar copper nitrate. Okay, there we go, 50 grams. So the masses here really don't matter. This here is copper. I shouldn't say that, that's not copper. That is zinc metal, even though it's orange. Zinc metal, still zinc metal. Zinc will be the excess reactant. And no matter how much I add in here, the copper is going to run out. So I can just draw copper, make sure you draw those charges on there. Nitrate, nitrate, copper plus 2, nitrate, nitrate. So I do 2 of them. These 2 will come up and they'll exchange. And if it's a 1-to-1 ratio between copper and zinc, so afterwards all my nitrates are still there, and my hold on. All right, I have a zinc 2 plus, zinc 2 plus, and I'd have a copper here and a copper here. We could label those guys, if you'd like, as copper metals. No charge. All right, how many liters of oxygen gas required to completely consume 3.6 liters of hydrogen to form water? Okay, let's do this here. Shifting gears, so we have O2 plus H2 yields H2O, 2 here and 2 here. All right, it says how many liters of oxygen, so this is what we're looking for in liters, and I'm producing how many liters of oxygen are required to fully consume 3.6 liters, 3.6 liters of hydrogen to form water. Now, we know that when we're doing our stoic ratios and stuff, we absolutely cannot use mass. Grams or mass in this situation is out. But it turns out that's pretty much the only thing you can't use. You should be aware that these PIV-NERT, so PeV equals nRT, that N equals PV over RT, and all these things are the same proportionally wise, so we can actually use liters here. And you'd show your work, okay, that proportional wise here. The answer is we're going to get 3.6 liters, and we're going to get require, what's half of that? That'd be what? 36 would be 18, 1.8 liters. And that's my answer. Now, again, I did not show work there, and anybody who's been around the block here with me for a little bit knows that you have to show your work. So be careful about that. So again, in the last one, all particles have different protons and different masses. So the mass doesn't work, isn't relative to the how much something weighs and how many there are. That's not a proportion that is consistent across particles. Let's reiterate that one last time. Is that, again, mass is deceiving, but liters is not. Under given conditions, if you have twice the volume, you have twice the particles. So we can use that proportion. Mass, you cannot. All right, and apparently it's a multiple choice problem, and there we go. All right, number 7 says, consider the reaction below. Exactly 6.2 grams of phosphorus gas and 4 grams of hydrogen gas are going into a vessel. How many moles of each gas is initially available? All right, so this guy is 2 grams per mole. So that means I have 2 moles. So 2 moles, this guy's out, this guy's out. All right, now we're down to these 2. All right, 6.2 grams of phosphorus gas. Okay, well, phosphorus. What's the molar mass of phosphorus? Let's just go check here. Phosphorus is 30.6 0.9 grams per mole, so almost 31. All right, so 30.1 grams per mole. So in this case, 30.1 grams equals 1 mole, or 3.01 grams equals 0.1 moles. So, and I have 6.2. So I have double that value. So rather than 0.1, I have 0.2. That's my answer. Therefore, I would believe A to be the answer. Just using proportional mathematics. Pretty important tool. All right, 6.2 grams of phosphorus, which is 0.2 moles. 4 grams of hydrogen gas, which is 2 moles. Form pH3, which is limiting. Okay. All right, so well, we have less of the phosphorus, so maybe think that's limiting, but the hydrogen use it like 6 times faster. So it's tough. So let's see what we got here. So P4 plus 6 H2 yields 4 pH3. And I'm just going to create an ice table. 0.22, and there are other proportions. I teach it this way, and I wouldn't assume that someone can do these proportions in their head. So let's do this here. Let's say 3 times faster. I'm going to still say the phosphorus runs out first. Let's try it. Minus 0.2 to 0 at a 1 to 6 ratio. All right, 6 times 0.2 times 6. 0.2 times 6 equals 1.2. All right, and minus 1.2, which means if I consume all this, I still have 0.8 in excess. Bingo, this is my limiting reactant. And it's going to be the phosphorus. Obviously, this is not a limiting reactant. All right. Next, number 9. All right, says we have a maximum number of grams of pH3. What is the maximum it can produce when the same stuff? Okay, so I know I made this ice table, but I'm going to add to 1 to 6, 1 to 4. So let's do the work here. 0.2 at a 1 to 4 ratio. 0.2 times 4. 0.2 times 4 equals 0.8. All right, makes sense. 0.8 moles, and then phosphorus times 30.1 is the actual grams. Says what's the maximum grams you can make? That's the actual math there. Is it possible to do that without the math? Times 30, 20.24 grams, 24. That's what I got. So, all right, so we got here 24 grams is what I got there. What is the maximum number of grams of pH3 that can be formed when 6.2 grams of phosphorus, okay, reacts with 0.4 grams of hydrogen gas? Now, I got 24 here, and I'm pretty sure I made a mistake here because I don't even have 24 grams of stuff. Important. All right, so think in mind. Now, let's just think about this here. I only have 6.2 in 4, so I only have 10 grams. I only have 10.2 grams of stuff. All right, and the reason I made a mistake here, I used the 30.1, which is the molar mass of, okay, I made a couple mistakes here. That's the molar mass of phosphorus, but it's P4, so that could be something I got to backtrack on to fix. Let's finish this problem up first here, which could change a bunch of stuff here. But either way, so we'll do the best we can. All right, so I have 10.2 grams, so I'm never going to have 45. All right, and you'll note that this is based on what I had originally. This is my limiting reactant, which is 6.2. So if you use up all 6.2 of it, then you have at least 6.2 grams of product, which means this guy is out and that guy is out, okay, which leaves only 7. So 6.2 grams of phosphorus and a little bit of hydrogen, answer would be 7. All right, so there were some errors in the previous thing here. Let's go up here and see if that affects anything. All right, so, well, here's the phosphorus gas, okay. And then, which is fine. That's fine, okay, P2, 4, okay. My moles of P2O4. So there you go. So that is going to be an issue here. I would want to divide that by 4. So I would have 0.2 moles of phosphorus but since there's 4 of them in there, I'll have to backtrack on that, and this will end up not being correct. And there we go. Maybe you caught that. All right, is it going to affect this problem? Well, this was already our limiting, so that means this guy is going to be down to 0.05. There we go. And then this guy will be 0.05, which means I'm only going to get 0.05 of these. And that is where my error happened there. 0.05 times 4. Let's try it to make sure. Good learning experience here. 0.05 times 4 equals, all right, 0.2. So I'm going to get 0.2 moles of my product. And my product does not weigh 30.1. All sorts of mistakes here. It's pH3. It's close. This guy is 30.1 plus 3 is 33.1. Okay. So the 0.2 times 33.1 equals 6.62. And therefore, this is correct. A hydrocarbon is burned, producing 20 liters of carbon dioxide and 4 liters of water. Which of the following hydrocarbons could be the reactant? Okay, so in this case, remember, carbon plus oxygen yields some hydrocarbon, CH. Yields carbon dioxide and water. So all of the carbon here, all the hydrogen in here. Okay. So you'll notice that I have a 2 to 1 ratio, or 1 to 2 ratio between these two species. So someone might jump to, let's say, well, this one per se. I mean, that's it. I don't believe that to be yet, because even though it's a 1 to 2 ratio here, there's actually 2 hydrogens in this one. So that doubles my hydrogen in this guy. So actually, it's 1 to 4 ratio. That guy's out. Therefore, this is the only option. This guy's out, and this guy's out. All right. Page. And we don't. Thank you very much.